recast this in a geometric language. But it turns out to be extremely useful in developing AdS CFT, finding more examples, checking the correspondence to find holographic duals of these extremization principles. And that's what I want to talk about in the rest of the talk. So this program started about 15 years ago, a bit under 15 years ago, in the context of Sasaki-Einstein geometry. So AdS CFT built using Sasaki-Einstein metrics. So let me remind you a little bit about that story. So, first of all, the Sasaki-Einstein, let me remind you, it's a Calabi-Yau cone. So you take it, in this case, a three-dimensional, Calabi-Yau threefold, and the metric is assumed to be of this conical form here. If it is of that conical form, then the cross-section of the cone, so this blue slice here, is a Sasaki-Einstein by definition. So you can give an intrinsic 5-dimensional definition, but that's the quickest definition of what a Sasaki-Einstein is. And if you put a stack of D3 branes at the apex of that cone, zoom in on the back reactor geometry, you get to this type 2b solution, AdS5 cross Sasaki-Einstein 5 with just 5-form flux, F5. And these are dual to n equals 1 supersymmetric conformal field theories in 4 dimensions. And there's an analogous story in D equals 11 using membranes at the apex of Calabi-Yau 4 cones. Now we have a cross section, which is a Sasaki-Einstein 7. And the back reactor geometry is now AdS4 cross Sasaki-Einstein 7. And just flux along the AdS4 directions. So that in both cases, they're not the most general fluxes that you could have, but it's a set of fluxes associated with these particular configurations. And once again, this is in the class of conformal field theories I was just describing. Well, given that they have, the field theories have an R-symmetry, the geometry better realize that R-symmetry before we even think about extremization. And it's a simple fact that the Sasaki manifolds have a canonical killing vector, and that is dual to the R-symmetry. The quickest way to see where that comes from is there's clearly a preferred vector here, d by dr. There's a complex structure. And if you act on the complex structure with that vector d by dr, you get another vector, and that vector gives rise to xi, which is the killing vector. So we knew that there had to be a canonical killing vector, and there simply is. But how are we going to do this extremization principle? Well, one more fact is that the acentral charge in the case of n equals 1, d equals 4 is inversely proportional to the volume of the Sasaki-Einstein 5. And in the three-dimensional example, the free energy on the S3, these are the quantities that appear in the extremization principles, is inversely proportional to the square root of the Sasaki-Einstein. So we want some way of writing the volume as a functional of the space of trial killing vectors. Now, an important point to appreciate at this stage is one has to invent the rules of going off shell. Everything I've said so far is an on-shell statement about gravity, but if we want a variation of principle, we have to go off shell somehow. And in general, there's no canonical way of doing that. But what Martellier, Sparks, and Yau said is that let's, instead of thinking about Sasaki-Einstein, let's just think about Sasaki. And that just simply means that the cone is no longer Calabi-Yau, it's just Kähler. Being Kähler, it still has an n+1, 0 form, psi. That means it's got, it probably should be n, but n holomorphic legs. dz1 wedge dz2 wedge dz3, and so on. And that holomorphic form doesn't vanish, is non-vanishing everywhere. So when you go off shell, you still have a Kähler cone still has that property. So what you do is consider the space of Kähler cone metrics, or Sasaki metrics equivalently. You choose a holomorphic killing vector xi, and a sort of a technical point, but it's important, is you hold the charge of this n+1 this holomorphic form to be fixed. C should just be 1 here. Or sorry, I think it should be n. Okay, so you do that. And then what you find, and this is where the work is, and I'm not going to describe the work, is you find that the volume of the Sasaki metric is just a functional of the choice of this holomorphic vector. So this is, when you view these expressions back here, the version of what's called volume minimization, and it's an inversion of the geometric extremization principle for those two principles, variation of A and variation of F. This looks very abstract, the volume form on the space of Sasaki-Einstein metrics as a function of holomorphic vector fields, where those vector fields are such that you're holding the charge of the holomorphic form fixed. But that's what it is. It looks abstract, it looks not particularly useful, but it's extremely useful. It's extremely useful because, and later I'll give you a flavor of why it's useful, but I won't explain why it's useful here. But it's particularly useful in the case of toric geometry. So it's useful for both, for identifying a bunch of conformal field theories. So the toric data can generate or describe a particular quiver gauge theory, and the toric data can allow you to do this geometric extremization principle, and you find agreement between the two. So supersymmetric AdS CFT was enormously developed using these results. And one more thing that's interesting is that all the motivation here was came from 4-dimensional field theories and 3-dimensional field theories. But this principle applies to arbitrary Sasaki-Einstein metrics. So even though a general Sasaki-Einstein metric has nothing to do with AdS CFT, these geometric principles apply to the whole infinite class. So yeah, you knew that there was going to be something interesting about 7-dimensional, 5-dimensional geometries, but you in fact deduced something about an infinite class of geometries. So that's of interest from a geometric point of view.
Jerome, one question, sorry to interrupt. So by going off shell, you mean that these geometries don't solve Einstein's equations? Is that
exactly.
Correct? Okay. Only at the extremum.
Exactly. So this extremization principle, at the extreme principle, it puts you back on shell. In other words, with all this extra data still there, you find the only little bit of data is just varying over the space of killing vectors, these holomorphic killing vectors.
Thanks. Okay,
so the recent progress is basically playing the same game for a class of AdS3 solutions with an R-symmetry, and a space of AdS2 solutions of AdS3 of 2b and AdS2 solutions of d equals 11. And the progress here has led to the identification of infinite new class of AdS CFT examples. This case is particularly interesting because this was a case where there is no field theory extremization principle known. So from the geometry, at least in the large n limit, we're saying that there is. And as a special subclass, it includes the I extremization, which I mentioned was a field theory extremization principle that was known in the large n limit. So that's some interesting sort of foundational questions here. And another point is these AdS2 solutions can arise as the near horizon limit of black holes in AdS, asymptotically AdS4 space. And in that case, the principle gives rise to a way of identifying the microstates of, or a way of counting the Bekenstein-Hawking entropy of such black holes. And I'll talk about that at the end. So let me tell you what these, the kinds of solutions that we're interested in are. In 2b, it's AdS3 cross Y7, and in D equals 11, it's AdS2 cross Y9. In both cases, you'll know that notice that it's a warped product because, in both cases, there's this capital B, which is a scalar. B is a function of Y7, and B here is a function of Y9. So this has all the isometries of AdS3 and AdS2, but it's a warped product because of the existence of this function B. In the 2B case, there's just 5-form flux. And notice that there's a 2-form here to make this a 5-form. And this is the Hodge dual of that. In the D equals 11 case, there's volume of AdS2, which is a 2-form. So the data in both cases is an odd dimensional manifold, a metric, a scalar function B, and a 2-form. And it's not clear from what, from just looking at these two expressions demanding supersymmetry, that they have anything in common. But what I showed with Nakwu Kim, I should say Nakwu Kim and his student developed this, studied these in the first place, and then together we realized that there are special cases of an infinite class of geometries. So this is sort of the analog of Sasaki-Einstein 5, Sasaki-Einstein 7, and then we observed that there's actually, they're part of an infinite family. In the Sasaki-Einstein case, that was trivial because they were just Clavier cones of different dimension. Here we had to sort of see what they had in common and then generalize it to arbitrary odd dimensions. Okay, so that's what we're interested in, that class of geometries. And in both cases, the flux is not the most general flux you could switch on, but it's a class of fluxes that is still extremely rich and is what we'll be focusing on. So back 15 years ago, roughly 13, 14, 15 years ago, myself and collaborators constructed lots of examples of these. And for people who know a little bit about the history, these constructions were roughly the analog of the construction of YPQ Sasaki-Einstein metrics. So you actually could be able to write down explicit solutions in closed form, everything in front of your eyes. But we didn't really know how to identify the dual field theories. So for the rest of the talk then, I want to tell you about this GK geometry, that is this data here that goes into building these solutions, what it actually is. Then go off shell, just like we did in the Sasaki-Einstein case, and then see or tell you about what the new extremization principles are, which are the dual to the C extremization and a new principle for supersymmetric quantum mechanics. And then at that level, it'll be a little bit like the abstract statements I just made for Sasaki-Einstein geometry. And then I'll say a little bit about how things become algebraic and completely concrete in the context of toric geometry. And then if there's time, which there may well not be, I'll try and say something about the recent work I did about putting supersymmetric field theories on a spindle. The spindle's a weighted projective space or an orbifold that's shaped like this. And if we have time, I can talk about that towards the end of the talk. Good. Any questions at this point? So let me begin then by telling you what this GK geometry is. So as I said, it's an odd dimensional manifold, a metric, a scalar, B. Don't think about B as a 2-form if you're just tuning in. Oops. B is a scalar field. And a 2-form. And the 2-form is closed. So GK geometry, one of the things it does is it extremizes this action. This may look complicated, but it's actually very simple. I'm just integrating over the odd dimensional manifold. There's an Einstein-Hilbert term, a cosmological constant term, a scalar term for the scalar, sorry, a kinetic term for the scalar, a Maxwell term for the gauge field, and there's this warp factor here. So you can extremize that action, and a GK geometry by definition has to solve those equations of motion. We want supersymmetry, and supersymmetry is the existence of certain killing spinors. And I won't write those down because I'll tell you what an equivalent geometric version of those killing spinors are on the next slide. And we also want to demand, certainly for the two examples we're interested in, the AdS3 and the AdS2 cases, we want to demand flux quantization on codimensional 2 cycles. So just let me remind you here. So the 5 form is given here. So we want the 5 form to be properly quantized on Y7. So that's going to give codimension 2. And star of F is going to be quantized on Y9. So it's just the standard quantization in 2B and D equals 11. And that gives rise to some condition on flux quantization on codimensional 2 cycles more abstractly. Good. So we solve those equations of motion and we have supersymmetry. And supersymmetry is equivalent to this data here. And there's quite a lot on this slide. So let's go through it slowly. So n is always bigger than or equal to 3. So the first example of GK is Y7, Y9, and so on. And 7 and 9 in the case of most interests. Supersymmetry implies that we have a canonical killing vector. And just like Sasaki-Einstein, we knew that had to happen. The way it arises is less direct than in the other case, but there definitely is a killing vector. And in the AdS CFT examples, it's dual to the R-symmetry. That killing vector has constant norm, norm 1. So it never vanishes anywhere. You can define a 1 form that's dual to that killing vector. So we just introduce eta like that. The metric can be now put into this canonical form. So it's the 1 form plus an even dimensional metric. And I've taken out a particular exponential of the scalar function b. And it turns out, rather remarkably, is when you do that, this transverse even dimensional metric is scalar. So it's scalar, it means it has a scalar form J and a Ricci form rho. And remind you that the Ricci form, if you take the Ricci tensor of a scalar manifold and you contract with the complex structure, you get a 2 form, and that is the Ricci 2 form. So this data of this transverse scalar metric is going to appear in the final answers, as we'll see. So we've got an odd dimensional manifold. A killing vector sort of pulls out one direction. There's an even number of transverse directions, and that those even dimensional transverse directions carry a scalar metric. And actually, the scalar metric has all of the information of the full solution, remarkably. So I had to tell you what B was and also what F was. Well, B is simple. B is just the Ricci scalar of the scalar manifold. So C here is just a number depending on n, and it doesn't play any important role, but it just floats about. So in particular, the only scalar manifolds, transverse scalar metrics that are important here are ones with positive Ricci scalar. Otherwise, this wouldn't make sense. The 1 form eta actually is determined by the scalar metric because its exterior derivative is just the Ricci tensor rho. And finally, F is given by the scalar form J plus D of e to the minus b eta. And as I just said, they are both determined by the scalar metric as well. So this scalar metric basically fills out the whole of the solution. Or in other words, if you had another way of saying it, and is if you want to actually construct explicit examples, if you had a scalar manifold with positive Ricci scalar, you could construct a solution. A solution with this supersymmetry. To get a supersymmetric solution to the equations of motion, we also have to satisfy the equations of motion, which was varying that action. And that was the Einstein equation, the scalar equation, the gauge equation, and so on. But remarkably, or maybe not remarkably, but with all this information of supersymmetry, almost all the equations of motion are satisfied, except for one equation, which turns out to be this one. So this is, again, the Ricci tensor and Ricci scalar of the scalar metric. And it's a box R equals Ricci scalar squared minus Ricci tensor squared. So if you have a scalar manifold or a calorimetric that satisfies that equation, you have a solution. So that's what GK geometry is, both supersymmetry and solving the box R equation. Any questions on that?
Yeah, so I have a question. If there's supersymmetry, shouldn't I expect first order equations?
So you mean this one?
Yes.
Yeah, so I mean, roughly speaking, supersymmetry implies most of the equations in motion up to the Bianchi identities. And the Bianchi identities and the field equations for the fluxes, when you substitute this data back in, gives rise to this equation. So yeah, that intuition just isn't correct.
Okay, thank you.
Jerome, may I ask, maybe
yes.
it's the same question in a different form?
Yeah.
So this equation you have in the red box is of fourth order, right?
Yeah.
Right. So how do we make this compatible with the Einstein's equations originally of the original system?
So one way of saying it is, so we have this expression for F, and we have some equation which is something like d star F is 0. That will be one of the equations of motion from the action I put up, just an ordinary Maxwell type of equation. But F, through supersymmetry, is now expressed in terms of, I mean, the Ricci scale is appearing here.
Okay.
So you take d star of F there, you've got two derivatives in the Ricci scalar, and it turns it out. That's probably a better answer. Better answer than the first answer that I made, because that makes it very concrete.
Okay, good. Thank you.
Okay, so to do an extremization principle, we have to go off shell. And as I said before, there's no one tells you how to go off shell. You have to just find something that works or is interesting. And what we did or have done is we keep all these conditions, all the conditions of supersymmetry, and relax this final box R condition. In fact, as you'll see, we keep an integral of it. But for the moment, let's just imagine we've just got rid of that. So this would be now the class of geometry we want to consider and see if we can construct the action as just a function of a space of holomorphic killing vectors, which will then be the principle of an extremization of the R-symmetry. So we relax that condition, and remarkably, we still have a huge, well, again, not remarkably, because that supersymmetry was a lot of conditions. We have a lot of structure to the cone metric. So I'm now going to consider, there's the odd dimensional manifold, and I consider this cone metric, which is not directly physical in the context of these AdS CFT solutions, but geometrically I want to consider that. And it turns out that this is an integrable complex manifold. Sorry, it's a manifold with an integrable complex structure. The R-symmetry vector is a holomorphic vector field on this cone. This cone has a nowhere vanishing n+1, 0 form that's closed. And the R-symmetry has, and psi has a particular charge with respect to that R-symmetry. So this should be reminiscent of the conditions we put in back in the Sasaki-Einstein story. And it's almost exactly the same with a few small little differences. So we have that structure. And in particular, this technical point is we're holding the charge of xi fixed. If we didn't hold that fixed, there wouldn't be a good variational principle, because you could just change the vector fields and your action could be made as small as possible without holding something fixed. So this is a technical point, but it's an important technical point. And it happened before in Sasaki-Einstein, and it happens here as well. So here is the extremization principle in a nutshell. We fix a complex cone, and we fix one of these n+1, 0 forms xi. sorry, psi, we fix a holomorphic, we choose a holomorphic vector field xi, and we hold the charge of psi fixed. We consider an off-shell GK geometry, that's with all the transverse scalar geometry and all the rest of those ingredients I put in. And the extremization principle, that is to get an on-shell GK geometry, turns out to be given by these three formulas here. So let's look at the last one first. The last one is the action, and the action can be written in terms of eta, the one form dual to xi, the Ricci form rho, and you soak up with a bunch of the Kähler form j's to make a 2n+1 dimensional form. And this is the action, which is just a functional, given this data, of the choice of holomorphic Killing vector. In other words, if I vary this functional as a functional of my choice of xi, satisfying these conditions, at the extremal point, I'll put myself on the shell, and I'm varying the action over the space of the dual R-symmetry vectors from the field AdS CFT point of view. To do that variational principle, it turns out, and to make it consistent, I need to impose this constraint. And again, this looks complicated. Eta, now it's rho squared. There was just one factor of rho there. Now there's 2 here and correspondingly a different number of j's. This equation is actually the integral of this equation. So if you integrate this, obviously the integral of box vanishes, and you're getting the integral of r squared minus Ricci squared. It's not completely obvious, but it's plausible, and it's true that that is what that equation is. So when I said we went off shell and we relaxed that condition, we actually, to make this a good variational principle, we have to impose that constraint. And finally, I mentioned flux quantization, and flux quantization is also written in terms of the same data. And again, this is not meant to be obvious, but it's now over a base of codimensional 2 cycles. It turns out that if you integrate this quantity and demand it's an integer, that is flux quantization. So this is the geometric version of the extremization principle. It looks very abstract, and if you have no experience in this, it looks kind of useless. And you think, oh, well, good for you. What are you going to do with that? But actually, it is very useful, as I'll try and give you an example.
Sorry, Jerome, may I ask at this point, because there seems to be then a relation between the action that you are extremizing and the fluxes that you integrate in order to get the quantized charges. Is there such a relation in general?
So this is an integral over codimension 2 cycles, and this is an integral over the whole manifold.
Yeah, but I don't mean the integral, but the flux. I mean the magnetic flux that you integrate to get the charge.
So you mean this integrand here?
Yeah, the integrand.
Yeah. So it's different to this. I mean, it looks the same, yeah, apart from some different values. I think, I didn't think there's a direct connection, just like this integrand also looks like this integrand, but there we're just imposing it as a constraint. I think the way I'd phrase it is more that it's, given we've imposed most of all of supersymmetry and most of the equations of motion, everything just beautifully ends up just depending on rho, j, and eta, or equivalently the choice of xi. That's what I'd say.
Mm-hmm. Okay.
Actually, I'm not quite finished, because I said the action was this, and if you extremize this, it puts you back on shell. But importantly, the on-shell value of S is actually physical. So the on-shell value of S is 1 on G3. I didn't mention that actually, so let me quickly mention this. When I wrote down these AdS3 and AdS2 solutions, I put an L in here. L was just an arbitrary constant, which is fixed by flux quantization ultimately. That's what that capital L is. And here, when you evaluate the on-shell action at the extremal point, you get that radius divided by G3, and that's just Heno and Brown, and that is the central charge of the dual supersymmetric conformal field theory. So this shows explicitly that this is the geometric version of C extremization. For the AdS2 X Y9, remember there's no dualization, there's no extremization principle in the field theory for these quantum mechanics. So what are we finding here? Well, we're finding that the action evaluated at the extreme point is 1 on the 2-dimensional Newton-Stott constant corresponding to the AdS2. And generically, we expect that that's giving us the logarithm of the partition function for the dual quantum mechanics. Also, if the AdS2 is the near horizon of a black hole, then this 1 on G2 corresponds to the Bekenstein-Hawking entropy of the black hole. So in that case, this variational principle is now a variational principle for black hole entropy. Now, we don't know the necessary and sufficient conditions for these geometries to arise as the near horizon limit of a black hole. But what I'm saying is when they do, this principle is corresponding to extremization principle for the black hole entropy. Good. So that's the the sort of the most general abstract result that we had. That you impose this data on complex cones, and then you do carry out this variational principle. At the extremal point, you recover central charges and black hole entropy, or the logarithm of the partition function for the quantum mechanics theory in the large N limit. So let me now demonstrate or try and convince you that this is actually useful as opposed to just being abstract formalism. So what I want to do now is focus on particular subclasses of examples. And I'll first look at AdS3 cross Y7. And the Y7 now will be a particular Y7. It'll be a fibration of a 5-dimensional manifold over a Riemann surface of genus G. So the first question you should ask, why am I focusing on this? And there's actually a very simple and nice physical picture. Let's imagine we started with a nice AdS5 cross Y5 solution of type 2b and a Sasaki-Einstein metric on the Y5. This is dual to a 4-dimensional supersymmetric conformal field theory. And you could do A extremization and work out what the dual field theory is using various brain technology that's known. And what we know is that the isometries of Y5 give rise to global symmetries. One of them will be the R-symmetry, but you could have additional global symmetries. 3 cycles of Y5 give rise to additional global symmetries called baryonic symmetries. So imagine we have one of those field theories, and we also have its gravitational dual. And now we compactify that 4-dimensional field theory on a Riemann surface. And we add magnetic fluxes for all the global symmetries. So the integral of the field strength along the Riemann surface is just some quantized integer. And a technical point which is well known is that if you put this field theory, supersymmetric field theory, on a Riemann surface, in general, you'll break supersymmetry. But there's something called a topological twist, which means that you just have to adjust these magnetic fluxes in a precise way, and particularly the R-symmetry flux has to be chosen suitably so that you preserve supersymmetry. So if you know that well. If you don't know that, just take it as when we compactify the 4-dimensional field theory, there's a little technical point that we have to make sure these fluxes are chosen generically up to ensuring that supersymmetry is satisfied. Okay, so we have a 4-dimensional field theory, we compactify on a Riemann surface, and we can now flow to a 2-dimensional conformal field theory on scales much larger than the scale set by the Riemann surface. If capital IF, if we actually flow to a field theory, a conformal field theory, then we expect its dual to AdS3 cross Y7, and Y7 is fibered this way. So this is the whole point of focusing on these geometries. It's because we have a very concrete physical picture of how they could arise. Start with your favorite four-dimensional quiver gauge theory, reduce on a Riemann surface, flow to a two-dimensional conformal field theory. If that also has a 2B dual, it should be of the form AdS3 cross Y7, and Y7 is fibered this way. So that's why we focus on these. Actually, let me just see if there's any questions on that before we go on. Good. So we have a nice picture. We also want to make things algebraically tractable. So now let's assume that Y5, this is the starting four-dimensional object, or dual to a four-dimensional field theory. The complex cone, the Calabi-Yau, is a toric Kähler cone metric. What does this mean? It means that the threefold has three commuting killing vectors. And there's beautiful toric geometry associated with this setup. The geometry of this Kähler cone can be specified by a polyhedral cone. I've drawn it there. There's a bunch of inward pointing normals to each of the facets. And those normal vectors are three vectors that have integer coefficients in this lattice. What do those little vectors tell you? What they tell you, or the way you should picture this, here's a little polyhedral cone, supplement it with three U1s. So that gives us a six-dimensional space. And as you go to each of the boundaries of the polyhedral cone, a circle is shrinking to zero. So just think of a two-sphere for a moment. When you go, think of a two-sphere as a line interval, and at the north and south pole, the circle has shrunk to zero. In that case, there's just one circle, and it shrinks to zero at one end of the interval, and it shrinks to zero at the other end of the interval. In this context, as we go to the boundary of this polyhedral cone, a particular circle will vanish in a smooth way, and which circle it is of the three circles here is fixed by the vector v. So if you know those vectors, you have almost a very graphical picture of what the geometry is, how things are contracting to give you a nice smooth space. Okay, so that data, the VAs, tells you a huge amount about the Kähler geometry. And the extremization principle I said for the AdS3 solutions across Y7, when Y7 is fibered this way, becomes purely algebraic in the VAs. So those abstract equations I wrote down turn into the following explicit algebraic equations. So this equation is really a major punchline, but there's quite a lot on here. So it's not the details, but it's the structure of this that I want to emphasize. First of all, is this thing called V, which is called the master volume for the fiber. And it's a functional of a three-vector B, which you should think of as the choice of R-symmetry vector. Remember, we have three U1s. So the R-symmetry is pointing in one of those three U1 directions. And that's what that vector B is. And this, on the right-hand side, I have a sum. And you'll see that there's these things, oops, two V's and a B, two V's and a B, two V's and a B, here and here with round brackets around those. V is a three vector, B is a three vector, B is a three vector. So that's a 3 by 3 matrix. And the round brackets is a determinant. So you calculate that determinant, so on. You add them up with these lambdas, and you'll notice the index on the lambda A is changing a little bit. Anyway, that is a completely concrete algebraic thing you can construct as a functional of the V's, that's telling you your toric data, and which I haven't put into the left-hand side, as well as the choice of B, and the lambdas are some Kähler class parameters. And the extremization problem I told you about now turns into this algebraic problem. So the supersymmetric action, it turns out, can be recast in just taking derivatives of this master volume with respect to the lambdas, respect to the b's, you do some sums. And this supersymmetric action, you should view it at this stage, it's a function of b, the choice of R-symmetry vector, and some lambdas and a's. The constraint equation can also be roughly written in the same way, and the flux quantizations can also be written in the same way, all in terms of this master volume V. And if you solve the constraint equation, and you can solve the constraint equation and these flux quantization conditions to solve for the lambdas and the a's in terms of the n's and the m's, and then the action just becomes a function of B, the choice of R-symmetry killing vector, the flux is N, the flux is M, the quantized magnetic fluxes, including the topological twist you switched on, the genus of the Riemann surface you switched on, and that should have a little vector on it, and the vector V of the toric data. So the main point about this, which is complicated if you haven't seen it before, is that everything is absolutely explicit and concrete. None of this abstract formalism that I was talking about before. So for arbitrary toric Y5 that goes into one of these fibrations to give a Y7, you can calculate the central charge explicitly. So this is a very big infinite class of examples. You can now compare the on-shell version of this action with the field theory action you would get. So remember, we are starting with a four-dimensional field theory. We reduced it on a Riemann surface. We can now do two-dimensional field theory extremization and compare it with gravitational extremization. And you find exact agreement. So the functional of all this data agrees from the geometry to the field theory. So that's a remarkable result. So at this point, I'm almost saying, well, this does provide an infinite class of examples where of AdS3 cross Y7, where we've identified the field theory.
Sorry, Jerome. About the previous slide, how you go off-shell in the field theory? I mean,
in the field theory, what you do is you say, I've got my quiver gauge theory. I know about all my global symmetries. I reduce on the Riemann surface. So I now have a two-dimensional field theory, but I don't know what my two-dimensional R-symmetry is. It's going to be a linear combination of all the possible global symmetries that are around.
Oh, okay.
And then I do the field theory functional that way.
Okay. Okay.
Okay, so this is almost a complete sort of dictionary between these infinite class of two-dimensional field theories and an infinite class of AdS3 cross Y7 geometries. Unfortunately, it's not a complete proof because I didn't say this until now, but the geometric variational principle will give you the action for the on-shell geometry provided it exists. But there can be obstructions. So you could do the variation principle, but there is no solution that it corresponds to. And a very simple diagnostic, and what can happen is you might go through the geometric procedure and say, oh, I've just derived a field theory that has negative central charge. Now, clearly that's nonsense, and that's nonsense because there is no particular solution. Now, before you think, oh, wow, everything I've said is kind of the empty set. How do you know there's any solutions? I want to emphasize we have explicit solutions, infinite classes of them. So I think this obstruction issue, or when there's non-existence, is going to be a very small set of measure zero in the big space. But exactly what characterizes it is an interesting open question. And similarly, in the field theory, there's a similar open issue. If you reduce it, and I mentioned it before, if you reduce the field theory on the Riemann surface, flow to the infrared, do you really get a supersymmetric conformal field theory, or do you flow off to some gap system or to some other infrared dynamics? Again, we don't know that. But generically, that won't happen. And generically, we'll have this infinite class of examples. there's an exact analog of this in D equals 11, and I'll just be very brief about this. We say now we take AdS2 X Y9, and we now think of Y9 as a Y7 fibration over a Riemann surface. And you can do exactly the same game, and algebraically it's very similar. And you find what the logarithm of the partition function will be for the dual supersymmetric quantum mechanics. If the AdS2 solution is the near horizon limit of an AdS4 black hole, then that will correspond or be a calculation of the corresponding entropy. In the field theory, I remember this, I mentioned this extremization of Hosseini and Zaffaroni. So for certain quantum field theories precisely of this form, four-dimensional field theories wrapped on a Riemann surface, that's when they said there is an extremization principle. It agrees exactly with the geometric version that we just stated. So anytime there is such an AdS2 solution that arises as a near horizon limit of an AdS4 solution, combining this field theory result with the geometric result, it's giving you a microscopic state counting for the entropy of the asymptotic AdS4 black holes. There's more to say on that, and I'm aware I'm just slightly rushing through this because I'm out of time. Yeah, I'm just going to leave that there and just quickly flash up one slide and then the last slide. This is just to flash up if anyone's interested. The other special class of solutions that we looked at was AdS3 X Y7 and AdS2 X Y9, where the Y7 is a three-sphere fibration over a Kähler-Einstein 4, or a three-sphere fibration over a Kähler-Einstein 6. So the Riemann surface is gone and replaced by Kähler-Einstein space. It turns out that you can recast those solutions as Psyche-Einstein fibration, not over a Riemann surface, but over a spindle. So you can replay all the extremization principle that I was describing before when I had Psyche-Einstein 5 fibered over Riemann surface, but now over a weighted projective space or the spindle, and everything goes through. And the reason why this is interesting, it's interesting for several reasons, but I'll just say one. It's interesting because we're taking a four-dimensional field theory and we're wrapping it on a singular space. And this is a new and novel thing that no one's looked at before in the context of AdS CFT, and things seem to be working. And let me leave it at that. I'll flash up my summary and outlook, and you can start reading that as I ask for any questions.
Okay, thanks, Jerome. So are there any questions?
Yes, I have a question about the spindle. So if you put your gauge theory on the spindle and being the spindle singular, do you find some manifestation of that? Is the gauge theory physics completely well defined, or? Yeah,
so great question. So the short answer is we don't know yet. We don't know what the rules are. And perhaps a zeroth order question is how is supersymmetry preserved? So in general, when you wrap on these Riemann surfaces, you have to do this topological twist, which I was describing before, where you switch on particular R-symmetry currents to make sure that supersymmetry is preserved. What you find is in these AdS3 solutions and AdS2 solutions that supersymmetry is not being preserved by the standard topological twist. So already at a zeroth order level, there's something new going on.
I think I'm worried about a more basic thing, and just not so much supersymmetry, but I don't know, are operators well defined at the singular points? You know, is the energy density finite, etc.?
Sure, I understand. So yeah, the way I'm answering it is the short answer is we don't know, but within the supersymmetric context, I mean, there are these nice the AdS3 X Y7 solution, maybe I didn't emphasize that. That is completely regular. The miracle is it's just how you view it. So the final two-dimensional field theory has a dual with the Y7 regular, and you can just go into AdS CFT and you're doing something. Starting with the four-dimensional theory, and you wrap it on the spindle. So in the UV, if you like, if you want to do a flow across dimensions, that's where you have the singularity. So somehow holography is completely smoothing out that singular structure. Now it's all your questions about the UV, and I don't know what the answer is. But what I can say is when you've flowed, then things are good. I can say one more thing is in some cases we actually have the UV. So it's AdS4 in the UV and AdS2 in the IR. And the full 4-dimensional geometry is like an accelerating black hole. And the boundary, the spindle, is sort of the conical defects that are causing the acceleration of that black hole. Sorry, David, I realize as I'm going off in this direction, it's going further from your question, because your question is purely a field theory one. And I'll just back up to where I said before. There's basic foundational questions which we don't know the answer to, but it could be in the context of supersymmetry. Well, it is in the context of supersymmetry, where those things will be better behaved and are the place to try and understand them.
Thanks.
Okay, Adolfo, you have a question?
Yeah. So you said in your talk that there was no prescription to go off shell in the geometric setup, and then you decided to do it by relaxing the equation box R equals blah, blah, blah. Do you understand why does it agree with going off shell in the field theory? Because you said you get the matching between the entropies off shell, not even on shell. So
yeah, it's a good question. I don't.
Both options are the
Yeah, it's very good. The short answer is I don't know. And you're absolutely right. It's indicative that there's more to be understood. I mean, you physically sort of going off shell, you might feel like you want to do some RG flow, but just like in the Sasaki-Einstein case, when you go from Sasaki-Einstein to Sasaki, that's not really RG flow because there's no Minkowski cross Sasaki solutions that you're following. So yeah, it's a good open question. I don't know the answer to that.
Thanks. Carlos, you want to ask?
Thanks very much, Jerome. So one remaining question that I had. So in the example, you explained the flow from 4D conformal theories to 2D conformal theories. So in 4D, we have the extremization of Martelli, Yau, and Sparks. In 2D, we have yours, right? The one you explained today. In the middle, do you, I mean, I know you lose the structure, right? You lose all the structure you are using. But do you think that there could be some quantity that behaves similarly in the flow? Because that would be, yeah, the central charge. Yeah,
it's a good question. It's a little bit like Adolfo's question. Well, there's some aspects of that. So these extremization principles are not following the RG flow, but I suppose, yeah, one's possibly might not need to go in that direction and just try and set up a more general extremization principle for the class of RG flow solutions. Yeah, it's a good question. I don't know the answer to that either.
Thank you.
That would be nice.
Are there other questions? Okay, then let's thank Jerome
Thank you.
in the way we can.